Precision measurements have overwhelmingly confirmed the ΛCDM cosmological model across the vast majority of angular scales. At small scales, the predictions align perfectly with the observed universe. Our window into the early universe began mapping temperature fluctuations with this, the COBE DMR map. 9 years later, WMAP delivered a much sharper view. It confirmed the exact same large-scale patterns COBE saw, proving these fluctuations were physical realities rather than instrument noise. Then came the Planck mission. Its high-resolution map definitively locked in 4 unexpected features at the largest angular scales, specifically at multipoles below L equals 30. This chart shows the angular power spectrum of the CMB. The solid line is the standard model prediction. But notice the left side, representing the largest cosmic scales. Below L equals 30, the observed data points drop below the theoretical curve. The universe has less power here than expected. Look closely at the very edge. The quadrupole at L equals 2 drops exceptionally low. There is also a strict imbalance in parity. Odd-numbered multipoles contain measurably more power than even-numbered ones at large scales, resulting in a temperature parity ratio of roughly 0.81. Finally, the spatial orientation of these large-scale waves is highly correlated. The preferred axes of the L equals 2 and L equals 3 multipoles align to within about 10 degrees. In a statistically isotropic universe, an alignment this precise should happen in only 1 to 3% of realizations. Each deviation is modest on its own, typically 2 to 3 sigma. However, their correlated persistence across 3 separate space missions suggests a unified large-angle structure that statistical isotropy does not anticipate. Mode identity theory derives these anomalies from the static topological shape of the universe. Specifically, the theory models the spatial universe as a 3-sphere quotiented by the binary icosahedral group containing a non-orientable Mobius surface embedded within it. This specific topology acts as a resonant cavity. Just as the physical geometry of a brass bell dictates its acoustic frequencies, this structural boundary determines exactly which wave modes can exist within the universe. This table compares the theory's predictions to observational data. By applying the mathematical constraints of this exact topology, all 4 major CMB anomalies can be derived from just one fixed geometric parameter and one single observer position. What has historically been dismissed as the axis of evil is simply a measurement of the universe's boundary conditions. The foundation of this model is the simply connected closed 3-manifold known as S3. This manifold has a strict specific scale, a curvature radius of 5.3 gigaparsecs. This radius is derived directly from the cosmological constant, lambda, through the de Sitter relation and the Laplace-Beltrami operator. The mathematics lock the scale at exactly 5.3 gigaparsecs. In standard equations, spatial curvature is treated as a time-dependent dynamic term that competes with dark energy. Here, the spatial curvature is a strictly static boundary condition. Because the distance redshift relation in this framework relies on the phase evolution of a standing wave rather than expanding physical space, the apparent spatial curvature parameter, omega k, is naturally forced to 0 in standard data fits. The absolute macroscopic boundary of S3 is strictly locked in place by the cosmological constant. To determine which wave patterns can form inside this cavity, we examine the quotient space. Out of all possible scalar harmonics on S3, only those that remain invariant under the binary icosahedral group can survive. These surviving harmonics are graded by their 3D polynomial degree, labeled as n. This diagram shows the Molien series for the invariant ring of the binary icosahedral group. It acts as a mathematical filter, dictating exactly which n degrees exist. This filter mandates that 5 even-degree shells, n equals 2, 4, 6, 8, and 10, are entirely empty. After the constant mode at 0, nothing exists until the first surviving shell at n equals 12. When we translate this 3D spatial gap to the 2D observational sky,
The last empty shell at n equals 10 corresponds directly to a characteristic CMB multipole of roughly L equals 29. This perfect geometric gap is the physical cause of the first anomaly. The broad mode density deficit we see near L equals 30 is the shadow of the missing shells. This also explains the anomalous quadrupole. Because shells 2 through 10 are deleted, the L equals 2 quadrupole is starved of its primary power sources, fed only by the weak trailing tail of the n equals 12 shell. One algebraic group constraint mathematically forces the broad low L deficit and sharply suppresses the quadrupole simultaneously, without requiring any fine-tuning. The topology possesses an internal structure as well, a totally geodesic two-dimensional sphere embedded directly within S3. A Mobius band is constructed on the surface via a specific boundary edge identification that reverses orientation. This animation shows the effect. Fields coupled to this non-oriental surface must satisfy anti-periodic boundary conditions. This means a wave traversing the strip is required to flip its sign to complete the circuit. In quantum mechanics, these anti-periodic modes are forced to maintain a higher eigenvalue floor than standard periodic modes. When this spectrum is projected via Gegenbauer polynomials onto the observer's sky, this higher energy floor systematically suppresses the even-numbered multipoles. When we sum the first 4 surviving Molien shells and weight them by the primordial spectrum, the increased energy floor for even parity modes pulls the total parity ratio down to exactly 0.81. The asymmetry is a direct measurement of the observer's distance from the domain center. Topology dictates the allowed modes, but the topology does not dictate where the observer stands within the fundamental domain. The theory introduces its single locality parameter here. The observer is positioned exactly 2.1 gigaparsecs from the domain center. From this precise offset coordinate, the radial profile further suppresses the L equals 2 component relative to L equals 3, locking the ratio at roughly 0.13. The invariant modes also possess inherent axial symmetry along the Mobius twist axis. This natively outgrinds the intrinsic quadrupole and octupole. We view this intrinsic axis from 2.1 gigaparsecs off-center. This displacement creates geometric parallax, shifting the apparent axis by roughly 8.6 degrees on our last scattering sphere. The 10-degree axis of evil is merely geometric parallax. We are observing perfectly aligned macroscopic structure from a slightly off-center address. 4 persistent CMB anomalies are strictly dictated by exactly one position coordinate. If the universe has this topology, why did the Planck mission's search for matched circles find nothing? Standard algorithms are built to detect orientable gluings with identical repeating temperature patterns, but under a non-orientable identification, the matching requires a strict sign flip. Conventional searches were never designed to detect an inverted thermal pattern. The CMB functions as the fundamental resonant pattern of a bounded cavity. Because this mathematical framework relies on fixed topological constraints, it is highly susceptible to falsification. The ultimate test lies in the overdetermination of our position parameter. The alignment angle, the quadrupole suppression, and the parity magnitude must all stem from the exact same location. Future polarization data from Lightbird and CMB S4 must yield parity asymmetries that resolve to the exact same 2.1 gigaparsec coordinate. In addition, Euclid Data Release 1 will independently test the companion predictions regarding a static cosmological constant and the phase clock. If independent observations require different spatial coordinates to explain these anomalies, the geometric framework collapses. But if they align, the anomalies reveal